Welcome everyone. In this video I'm going to show you how to get the Schmidt factors for an FCC phase using the Euler angles. So in my previous video I already showed you what we can do with the Euler angles and how we can represent different orientations using it, and how we can switch between different coordinate systems. Because the Euler angles are basically used for describing the rotations between two coordinate systems. And in this video, these two coordinate systems are the specimen coordinate system and the crystal coordinate system. So by using the Euler angles, we can generate a so-called orientation or rotation, or sometimes it's called transformation matrix. So this big guy here is the orientation matrix. It's usually denoted as G, phi1, capital Phi, and phi2. And these three Greek letters are representing the three Euler angles, and those are here in the formula. And then you can see that we have like 3 columns and 3 rows. So this is a 3 by 3 matrix. And what we have here is basically, in the previous video I showed you this matrix already, but this is a combination of 3 consecutive rotations, and this rotation will bring you from one coordinate system to another. One extra thing that you can get from this is the HKL and UVW values. So you can generate these two set of numbers as well from the Euler angles. But why we need this is that we want to bring the external stress, which is represented in the coordinate system of the specimen, into the crystal's coordinate system. So what we have to do is that we have a stress, let's call it sigma, and that is our stress represented in the crystal's coordinate system. So that is what I drew here on the right side of this image. So what we have here is we have the orientation matrix, which is this guy up here, and then that is multiplied by a vector. Now it's called S, and then the S vector can be, for example, 1, 0, 0. What that means is that if we have, let's say, a slab, or we have our specimen, something like this, then of course it has its own coordinate system, and it's usually, it depends on how you define it, but usually like this is the x-axis, this is the y-axis, and the one which sticks out from the plane is the is the z-axis, or sometimes they say that this is the rolling direction, this is the transverse direction, and then this is the normal direction. So you take these, and then for example, if S equals 1, 0, 0, that means that the x component is 1, the y component is 0, and then the z component is 0. So this means that, for example, if you have your specimen aligned like this, and you say that your stress is acting in this line, so basically it's a pure uniaxial stress, which is like acting in this direction of your specimen. So for example, if you have a tensile test and you want to represent the tensile stresses in your crystal coordinate system, then usually you use, for example, the 1, 0, 0 coordinates. But this can be made into more difficult cases when you have multiple stresses acting at the same time. And at the end, instead of using this simple 3 by 1 vector, you can represent the stress state with a 3 by 3 matrix. But here we don't care about that at this moment, or in this video. I just tell this example that we have the x-axis here. We picked that as the tensile direction, or the direction of the stress, and we try to represent that within the crystal's coordinate system. So to bring this stress into the crystal's coordinate system, we just have to multiply this by this G matrix. And each pixel on your image, you can see these images down here, each pixel of your image has a G matrix. So you have to do this kind of mathematical stuff for each of your pixel. And then for each pixel you will have a sigma matrix, or sorry, a sigma vector, which represents the stress within the crystal's coordinate system. And then we want to know the Schmidt factor. I already showed you an example where you can calculate the Schmidt factor by having the vectors already, but here we don't have some of the vectors, or more specifically, we have the n and the d vector because they come from the slip system, and we know that this is an FCC material that we are going to examine, and we know that that has 12 slip systems, and therefore we can know these planes and the directions within the planes, but we don't know the sigma, which is the stress in the coordinate system of the crystal. So that's what we get from this kind of equations. So for the Schmidt factor, we always have this cosine phi and cosine lambda. Cosine phi represents the angle between the stress and the normal vector of the plane, and the cosine lambda represents the angle between the stress and the slip direction within in the plane. So this is basically this so-called cosine similarity equation. So up here, this is a simple dot product. I'm not going to explain it how it goes, but the first component of this times the first component of this plus the second component of this times the second component of this plus the third component of this times the third component of this vector, and then you get a scalar, so a single number, and that's what you put here. And these are the magnitudes. This is always changing, and it depends on the components of the sigma, but the magnitude of a vector in this case is basically square root of a squared plus b squared plus c squared. So that comes here, and for this is the same, but we know that we are in an FCC system. So let's say we are in FCC, and that is always like something like 1, 1, 1 plane. Even these components can be negative, but if you multiply it by itself or you square it, then it becomes a positive number anyway. So you know that this squared, this squared, this squared, if you just sum them, that is always 3, whatever the sign is here. So we know that we can fix this value to square root of 3, and then you just do this mathematical stuff. And the same applies here. So this is a scalar, but now instead of using the numbers for the plane, you use the numbers for the directions inside the plane, and here also, but we know that again we are in FCC and we are curious about the slip directions, not the twinning directions. So these is usually you have 2 1 component and 1 0 component. I just don't remember the signs at this moment, but sometimes one of this component can be -1, but whatever you do, this will be always square root of 2 at the end. So this can be fixed. I already wrote it here, and we can do this mathematics. One thing that can be important to take care of is that how you define the angles. So when you start this whole thing, basically it depends on your Euler angles, but you have to know whether you defined your angles in degrees or radians. That's very important. So I just put a note here, dig versus rad. So this is very important, because if you mess it up, then you will get some funny numbers, and you obviously want to avoid that. So down here you see two maps. So the left-hand sided map here is based on the Euler angles. So I just adjusted the RGB, so the red, green, blue values based on the Euler angles. So this is what you see, and here I mixed two phases of this material. This is a dual phase or duplex steel that you are looking at, and some of the phases are here face-centered cubic, and some of the phases here are body-centered cubic structure. So I wrote a software for this, so I will show it to you. But I want to show you that we can pick some grains. We can pick the Euler angles for that grain, and then we can calculate the Schmidt factor and then associate it to the grain. And on the right hand side, I separated the FCC grains, so only the FCC grains are colored, and the gray parts are just the BCC grains. So now at least you can see how nicely we can separate the two phases. But what we have here is just the FCC phase and the corresponding grains. And I will also show you the different grains. I will pick, I don't know, several grains and check the Schmidt factor for that, and we will see how it works. But I want to show you something else, because I made a table for this stuff. So it's more easy to do the calculations. So this is the table, and all we have to do is that we take the three Euler angles. I already filled in something in degrees. So we write in the three Euler angles, phi1, capital Phi, and phi2. And then I convert it into radians. So it's just the mathematical operation. It's basically the angles times pi divided by 180. So that's how we get the radians from degrees. And then we calculate the orientation matrix. So here you can see the wall matrix, and this is what we need only, and that is based on the equation that I showed you. And we can also just check some other numbers. I calculated the determinant of this matrix, and also, as I showed you, we can extract the HKL, which is basically this column here, and the UVW numbers, which is here. We have to normalize this in order to get back in the same manner as we usually see the Miller indices, like 110 or something, but I'm just not interested in that at this moment, but I showed you in some other videos how to do that. So yeah, we have the angles, Euler angles in degrees, we convert them into radians, and then we do the calculation and get the components for the orientation matrix. So far it should be clean, and it should be clear. So then here comes the bit more complicated stuff. So here we define a stress direction, and as I said, it will be 1, 0, 0. And then I just put the orientation matrix here again, just to see it. So what we do here is we multiply these numbers with this matrix, and then we get these numbers. So for a particular pixel of the picture that I showed you a minute ago, these are the components of the orientation matrix, and this is the these are the three components of the stress vector, which is the stress represented in the crystal's coordinate system. And then here we just calculate the lengths. I showed you how to do that, and luckily it's 1, so that's very nice. And here in these bigger tables, you can see the 4 different slip planes, which are defined for an FCC material, and each slip plane has 3 slip direction. So that's what we did here. So I defined the plane and I defined the direction, and then I calculate the cosine phi and the cosine lambda, and then it's just a multiplication between these two, so cos phi times cos lambda, and I take the absolute value of it, and we get the Schmidt factor. And basically this is all. And then we just have to repeat this 11 more times. So we pick the second option with another slip direction within the 1, 1, 1 slip plane, and we get the Schmidt factor. Then we move to the number 3 case, which is still the same 1, 1, 1 plane, and another direction here, and another Schmidt factor. And then we move to the next plane and repeat, and next plane, repeat, and so on. So this is for FCC. And what I do here, here on the bottom, I just pick all the 12 Schmidt factors just to see them in a better way. And then here, I just took the largest one. So this is all. So the basic procedure is to get the 3 Euler angles. You have to know your stress direction in the specimen's coordinate system. Then first, based on your Euler angles, you calculate the orientation matrix. Then when you know the orientation matrix, you can calculate the stress represented within the crystal's coordinate system. And then it's just the pure mathematics part. So you know your 3 vectors, the stress direction, which is here. You know the plane, that's the second, and you know the third vector, which is the direction, and then you just do the calculations for the cosine, and then finally you get the Schmidt factor. You repeat it, and then you get you pick the largest one with the largest absolute value, and then that's all. Why you take the absolute value? Because we don't care about the directions, whether it is a compressive or tensile direction, and as far as I know, the only difference between the negative and the positive Schmidt factor is that either you represent the tensile or compressive directions within a slip plane. So that's all. We have this, and now we can play around with the software. And what I will do is that I will also check another software. So first I will check the numbers from that. I will tell you. Then I pick my own software, click on a picture, on an element of a picture, and we see if we get the same numbers. So I put my software here, and as you can see, we have a Schmidt factor somewhere, and then this is the x and y coordinates, and then we get the slip system defined for the largest Schmidt factor. So I actually remember that I took these 3 Euler angles for the example from this grain, and if you remember, then the value of the Schmidt factor was 0.4. Now we round up for just 1 decimal, so let's see what we have here. So I click it, and you see it's 0.4. So now I check it with something else, and let's pick this grain. So this grain here should be around 0.5. So if you round these numbers up, so then this becomes 0.5. The software which I see it, which I check these numbers, is just using 2 digits. So since I don't have this digit in this software, the last one, then that software already rounds up this to 0.5. So let's check this blue thing here, and let us see what's that. So that should be 0.28, and in fact it is 0.28. So now let's check something. Let's check this. So I can tell you that this should be something like 0.34, almost 0.33. Yeah, it depends on where you click exactly, but it's close enough, I would say. And then let's pick this grain down here, and then this should be 0.32, and it is 0.32. And I don't know, I can pick all the grains in fact, but let's just check something else. So for example, this should be 0.45, and it is. If you round this up, then this becomes 5, so 0.45. Let's check the last one, which, let's say this should be 0.39, and it's 0.39, 0.4, depends on where you click again. You see, I just clicked another pixel, and then it became 0.394, and if you round this, then this is 0.39. But then I can like search more. Yeah, if I click this pixel, then it's 0.395, which becomes 0.4 if I round it up. So yeah. And what else we can see? Let's see this pixel. So if I check that, that should be 0.42, and it is 0.42. So we could see that this works as it should. So now we know how to get the Schmidt vectors from the Euler angles. So as you can see, it's quite easy. You can even have an Excel sheet to calculate all the stuff for you. But that works only for just one particular pixel of the image, which is not so effective. This map that you can see can be generated in like half a minute, because you have to calculate all these G matrices for each pixels, and this is I don't exactly remember, but roughly 200,000 pixels, so it's a lot of pixels. And of course you have to do 200,000 matrix multiplications, and so on and so on. So it's a lot of operations, but half a minute is not too much time for it. So it's not a long time. So as you could see, just to repeat, we could get the orientation matrix from the Euler angles, and then from that we were able to represent the external stress in the coordinate system of the crystal, and by using that stress and using the slip systems, which consist of different slip planes and slip directions, we could calculate the Schmidt vector, which is basically the largest absolute value among the 12 different slip systems. So that's all. I hope that this video and demonstration was useful for you, and you were able to learn something. I shared this table, so if you want to calculate your own stuff, or you want to practice or check your calculations, you can find the link in the description. But in exchange for that, I just want to ask you to subscribe to my channel. So it's just one click for you. So please do that, and I will continue, or I will try to continue providing these kind of tools for you, so you can use it for your studies or for anything that you need it. So yeah, I hope that this was useful for you, and see you in the next video.